For most diesel locomotives, shutting down is straightforward. You bring the throttle to idle, cut the fuel, and the engine winds down. The procedure takes moments and requires little thought. But on certain Baldwin AS-16 units, crews discovered something peculiar. If the main reservoir air pressure had dropped too low, the locomotive refused to complete its shutdown sequence properly. The control systems wouldn't reset, the interlocks wouldn't clear, and in some cases, engineers found themselves in the strange position of having to build air pressure back up just to shut the engine down. This wasn't a defect in the conventional sense. It was a consequence of how Baldwin designed these machines, and it reveals something important about why Baldwin ultimately lost the diesel locomotive market despite building genuinely capable equipment. Baldwin Locomotive Works had been building steam locomotives since 1831. By the time dieselization began in earnest after World War II, they had over a century of experience constructing heavy, mechanically complex machines that required skilled crews to operate properly. Steam locomotives demanded constant attention. Firemen managed the boiler. Engineers balanced steam pressure, cutoff, and throttle. Crews understood that these machines had procedures, and deviating from those procedures caused problems. When Baldwin transitioned to diesel production, they carried this philosophy with them. They assumed that railroad crews would continue to be skilled operators who understood their equipment intimately. They designed locomotives that were mechanically robust and powerful, built to the same heavy-duty standards that had served them well in the steam era. The AS-16 emerged from this thinking. Introduced in 1950, it was a road switcher intended for mixed service, equally capable of switching yards and hauling road freights. Baldwin equipped it with their own 608 SC prime mover, a turbocharged inline 8-cylinder engine, producing 1,600 horsepower. The locomotive weighed approximately 248,000 pounds and rode on two-axle trucks, designated A1A, A1A, with the center axle unpowered to reduce axle loading. Baldwin built the AS-16 the way they built everything: substantial, durable, and engineered to last. The frame was heavy. The running gear was robust. The engine itself was derived from marine and stationary power plant designs, where longevity mattered more than ease of maintenance. What Baldwin didn't fully appreciate was that the diesel revolution wasn't just about replacing steam with internal combustion. It was about changing the entire operational philosophy of American railroads. Diesel locomotives were supposed to be simpler. They were supposed to require less crew expertise, not more. They were supposed to run with minimal fuss, and that's where Baldwin's assumptions began causing problems. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. The heart of the AS-16's operational peculiarities was its starting system. Unlike most electromotive division locomotives, which use large electric starter motors powered by the battery bank, Baldwin employed a compressed air starting system on many of their diesel designs, including the AS-16. Air starting was not unusual in the broader world of internal combustion engines. It was standard practice in marine propulsion, where large diesel engines were routine, and in stationary power generation. The principle is straightforward. Compressed air stored in reservoirs is directed into the engine cylinders in the proper sequence, physically rotating the crankshaft until combustion takes over. For Baldwin, this approach made sense. They were already building locomotives with comprehensive air brake systems, adding air reservoirs and the necessary valving for engine. Starting seemed like a logical extension of existing infrastructure. Air starting also offered certain advantages. It could spin a large engine reliably in cold weather. It didn't depend on battery condition. And it was mechanically simpler than designing a starter motor large enough to turn over a 3,000 cubic inch diesel engine. The AS-16 carried dedicated starting air reservoirs, separate from the main brake system reservoirs, though both were charged by the locomotive's air compressor. When the engineer initiated the starting sequence, air flowed from these reservoirs through a distribution system that admitted compressed air to each cylinder in firing order, rotating the engine until it caught and ran on its own power. This system worked well under normal circumstances. The air compressor kept the reservoirs charged, and starting the engine was generally reliable. But here's where the design philosophy created unintended consequences. Baldwin integrated the air system into more than just engine starting. Certain control functions and safety interlocks also depended on adequate air pressure to operate correctly. This was consistent with Baldwin's steam-era thinking, where air pressure was always managed as a critical system parameter. But it created dependencies that crews accustomed to EMD and ALCO locomotives didn't expect. The issue with shutting down certain AS-16 units stemmed from this integration of air pressure into the control logic. On a typical EMD locomotive of the era, shutdown was electrically controlled. You'd move the fuel cutoff lever, the fuel injection would cease, and the engine would stop. The electrical systems would reset to their standby states. Air pressure in the reservoirs was essentially irrelevant to this process. On affected AS-16s, certain control interlocks were pneumatically actuated. These interlocks served safety functions, preventing the locomotive from being placed in certain conditions without the proper prerequisites being met. When air pressure dropped below specified minimums, these interlocks could fail to reset properly during shutdown. The locomotive would stop running, but its control systems wouldn't return to the correct standby configuration for the next startup. This created a frustrating scenario for crews. After a long run with heavy braking, the main reservoirs might be drawn down. Normally, this wouldn't matter for shutdown. But on these Baldwins, engineers learned that attempting to shut down with depleted air could leave the locomotive in an improper state. The next crew might encounter difficulty starting the unit, or the controls might not respond as expected until the situation was diagnosed and corrected. The practical solution was counterintuitive. Before shutting down, experienced crews would let the air compressor run until reservoir pressure recovered sufficiently. Only then would they proceed with the shutdown sequence. This ensured that all pneumatic interlocks had adequate pressure to reset correctly. From a purely technical standpoint, this made sense. The system was designed with certain pressure thresholds, and operating within those thresholds produced correct behavior. But from an operational standpoint, it felt absurd. Engineers expected to shut down their locomotive and walk away. Instead, they sometimes had to nurse the air system back to health first. The problem wasn't universal across all AS-16s or all conditions. Well-maintained units with tight air systems rarely exhibited the issue, but as these locomotives aged, as valve seals wore and piping developed minor leaks, the problem became more common. Cold weather exacerbated things, thickening lubricants and causing valves to respond sluggishly. Railroad crews are practical people. When equipment has quirks, they develop workarounds. The AS-16's shutdown peculiarities became part of the informal knowledge that experienced engineers passed along. The primary adaptation was simple: awareness. Crews learned not to dump their air before attempting shutdown. On other locomotives, it was common practice to make a heavy brake application while tying up the locomotive, bleeding down the train line and reservoirs as part of securing the consist. On AS-16s, experienced crews avoided this, keeping reservoir pressure up until after the engine was properly shut down. Senior engineers developed a feel for when the air system was healthy enough to proceed. They'd glance at the gauges, listen to the compressor cycling, and know whether the unit was ready to tie up or needed a few more minutes to build pressure. This knowledge wasn't formally documented in most cases. Baldwin's operating manuals explained the systems in technical terms, but they didn't always make the practical implications clear to crews more familiar with EMD practice. The result was a knowledge gap between experienced Baldwin operators and those encountering these locomotives for the first time. Transfer. Crews moving between different railroads or different locomotive assignments particularly struggled. A hogger who'd spent years on Geeps would approach an AS-16 expecting it to behave similarly. When it didn't, frustration followed. Some crews simply labeled the locomotives as troublesome and requested different power when possible. This reputation spread through the railroad community. Baldwins became known as fussy or temperamental, not necessarily because they failed more often, but because they demanded a different kind of attention than crews expected from diesel power. The great dieselization wave of the late 1940s and 1950s wasn't just about fuel efficiency or power, though both mattered. It was fundamentally about reducing operating complexity. Steam locomotives required roundhouses, water facilities, coal handling infrastructure, and highly skilled crews. Diesels could be refueled quickly, required less specialized facilities, and were supposed to be operable by anyone with basic training. Electromotive Division understood this completely. Their F units and GP series were designed around the principle of operational simplicity. Standardized control stands meant crews could move between units with minimal adjustment. Reliable electric starting meant consistent behavior regardless of air system condition. Modular construction facilitated maintenance. EMD marketed their locomotives not just as machines, but as systems that fit into an operational philosophy. Alco also grasped this concept, though their execution was sometimes uneven. Their RS series road switchers were generally straightforward to operate, and their later designs showed increasing attention to crew ergonomics and maintenance accessibility. Baldwin, by contrast, seemed to believe that locomotive quality was about mechanical durability and raw capability. They built strong machines. Their engines were robust. Their frames were overbuilt by EMD standards, but they paid less attention to the day-to-day experience of crews and maintenance personnel who would live with these locomotives for decades. The shutdown issue with AS-16s was symptomatic of this broader problem. Taken in isolation, it was a manageable quirk. Experienced crews handled it routinely, but it represented a philosophy mismatch. Railroads in the 1950s were trying to simplify their operations, reduce training requirements, and standardize procedures across their fleets. Baldwin was still designing locomotives as if crews would adapt to the machine rather than expecting the machine to adapt to operational preferences. When purchasing officers compared offerings from EMD, Alco, and Baldwin, the technical specifications might look similar, but the feedback from operating departments told a different story. EMD locomotives required less specialized knowledge. They caused fewer unusual situations. They fit more smoothly into the emerging diesel-era operational model. This difference influenced procurement decisions far more than any single technical feature. The AS-16 was produced between 1950 and 1953, with Baldwin building 127 units for various railroads. This wasn't a large production run by EMD standards, where individual model variants often numbered in the thousands. It reflected Baldwin's shrinking market share during the critical dieselization years. By the mid-1950s, Baldwin was struggling badly. Their domestic locomotive production essentially ended in 1956. The company that had been the world's largest locomotive builder for decades couldn't compete in the diesel market they had helped pioneer. The reasons for this failure were multiple and complex. Baldwin's late commitment to diesel development left them perpetually behind EMD's technology curve. Their prime movers, while sturdy, were heavier and thirstier than equivalent EMD engines. Their electrical systems, sourced from Westinghouse, were generally capable but didn't benefit from the same integrated design philosophy that EMD achieved with their in-house components. But beyond the technical comparisons, Baldwin suffered from an inability to adapt their institutional culture to diesel-era requirements. They kept building locomotives like steam power, expecting railroads to accommodate their engineering preferences. Meanwhile, EMD was asking railroads what they needed and designing locomotives to fit those requirements. The AS-16's air system quirks were a small piece of this larger pattern. No single design decision killed Baldwin, but the accumulation of such decisions, each reflecting a certain inflexibility in thinking, collectively made Baldwin products less attractive despite their often genuine mechanical merits. The 127 AS-16s found homes on various railroads, with the Pennsylvania Railroad being the largest customer. These locomotives worked in the mixed service roles Baldwin intended, handling road freights and heavier switching assignments throughout the 1950s. As with most first-generation diesels, the AS-16s faced replacement during the 1960s as railroads standardized their fleets around EMD and, to a lesser extent, Alco power. The unique characteristics that made Baldwin's challenging to operate also made them expensive to maintain, as parts became scarce and personnel familiar with their systems retired or moved on. Most AS-16s were retired and scrapped during the 1960s. Unlike EMD-F units and GP7s, which remained in service on short lines and industrial operations for decades, Baldwin road switchers disappeared relatively quickly once the major railroads finished with them. The same operational quirks that frustrated crews on Class I railroads made them unattractive to smaller operators who couldn't afford specialized knowledge for a handful of oddball units. No AS-16s are known to survive in preservation. The type exists now only in photographs, technical documentation, and the memories of those who operated them. Technical capability alone doesn't determine whether a design succeeds. Equally important is how well it fits into the operational context where it will be used. Baldwin built locomotives that were mechanically sound with durable engines and strong frames. Air starting was proven technology with real advantages. Pneumatic control interlocks provided genuine safety benefits. But these features didn't match what American railroads needed during dieselization. Railroads needed simplicity, standardization, and locomotives that any qualified engineer could operate without specialized knowledge. EMD provided exactly this. Their locomotives weren't necessarily better engineered in every respect, but they were better suited to how railroads actually operated. They required less explanation, less adaptation, less tolerance for quirks. The AS-16 didn't refuse to shut down. It simply required crews to understand the air system's needs and follow procedures that made sense within its design philosophy. That understanding was available to anyone willing to learn. But by the 1950s, railroads had decided they no longer wanted locomotives that required explanation. They wanted machines that just worked. Baldwin couldn't provide that, and their disappearance from the locomotive market followed with industrial inevitability. The air start shutdown issue was a small thing. Many crews handled it routinely, but small things accumulate, shape perceptions, and influence decisions. In an industry undergoing rapid transformation, they can determine which companies survive and which become footnotes. Baldwin became a footnote. Their locomotives have passed almost entirely from living memory. What remains is the lesson. Engineering excellence without operational wisdom is not enough.